Alright, so welcome back. We are going to be talking about some actual applications of the derivative with some sort of natural examples. So, for example, say there was a very tall, 400-foot tall building and you were to fall off of it. How fast would you be going when you hit the ground? So here's a picture of a building with a little person falling off of it. And then, you don't know why yet, but here's an equation for how far above the ground you are at any given time. So we often use S for position, and so S of t is 400 minus 16t squared. And so that's your position at any time, where t, time, is in seconds. Okay, so we're trying to figure out how fast we're going when we hit the ground. And so some of the things we have to think about are, one, what is the time when we hit the ground? And two, could we possibly figure out the velocity function so that we can use that time to plug into it and then get the answer? Well, ground level is when the position equals 0. And so let's just set 400 minus 16t squared equal to 0, which is the same as 16t squared equals 400, which is the same as t squared equals 25. Okay, so when t squared is 25, that means t equals 5 seconds. So we wind up hitting the ground after 5 seconds. So now we need to figure out how to find the velocity. Well, if we take the derivative of distance, the derivative of distance is the change in distance over the change in the main variable. And here our variable is time, and so we get change in distance over change in time, and that should actually give us the speed, right? Speed is how far you go and how long, right? And so the change in distance over time is speed. So we get, when we take the derivative, negative 32 times the time. And again, that gives us the velocity since it's the derivative of distance. And so what we're going to do is we're going to go ahead and plug in 5. And so negative 32 times 5 is negative 160 feet per second. That's how fast we're going to hit the ground. So here's another example. Suppose you have an object hanging from a spring, and I give you a position function for it. That position function is 3 minus sine of pi times time. And I ask you, at what times is the object stopped? So here's a picture of an object hanging from a spring, bouncing up and down. And asking when something is stopped is like asking when is its speed equal to 0. And something has speed equal to 0, well, if we took the derivative again of position, that would give us its speed, and all we'd have to do is set that equal to 0. So we take the derivative, and we get the derivative of sine is cosine, so we get negative cosine of pi t times the derivative of pi t. Remember, since it's not just sine of t, we have to use the chain rule. And so we get negative pi cosine of pi t. Well, we need to set that equal to 0. Remember, that's the speed, and so we're going to set the speed equal to 0. And remember, cosine is 0, right? Cosine of an angle is 0 if that angle is, well, pi over 2 or 3 pi over 2 and so on, right? But our theta isn't just a theta, it's actually pi times t. And so we need to set pi times t equal to pi over 2 plus k times pi. And if we divide both sides by pi to get t by itself, Well, all those pi's everywhere cancel, and we get that the time is 1/2 plus k, and here k can be 1 or 2 or 0 or -1 or -2. And so we get a possible list of times. Time equals -1/2, time equals 1/2, time equals 3/2, and so on. All right, here's another nice question that I like to ask, which is if we have a particle, and the particle is only moving horizontally, so it's moving left or it's moving right, and that's it. And I give you its position, x of t equals t cubed minus 12t. And I tell you that the time that we're going to care about is all of the times between 0 and 4. So we're going to start looking at this particle at 0 seconds, and we're going to watch it until 4 seconds and see what it does. And we're going to ask, during this time, how far does it travel? Well, so you can see in red there, we have a possible path of our particle. It might move left, and then right, and then left again. And anytime it changes direction, it stops for a second. That's going to be important because between any two stops, it's going to move a calculatable distance. So for one thing, we should look at its speed, and its speed is equal to the derivative. So we take the derivative, and we get 3t squared minus 12. We can pull out the 3, and we get 3 times t squared minus 4, which is 3 times t minus 2, t plus 2. Well, let's figure out when it stopped. It stopped when the derivative, or the speed, is 0. Well, that is 0 whenever t is either plus or minus 2. So it stopped when t equals -2 and when t equals positive 2. Well, when the derivative is positive, it moves to the right. And when the derivative is negative, it moves to the left. So let's go ahead and set up a little table and figure out when it's moving to the right and when it's moving to the left. Well, 3t squared minus 12 is a parabola, and so when we fill in the sign chart, we get that the derivative is positive until -2, and positive again after 2, and it's negative between t equals -2 and 2. So it's going to start off moving to the right, then move to the left, and then move to the right again. However, we only really care about time 0 on. So time 0 on happens here, and so the particle's actually starting off moving to the left. And so if you look at the line I just drew, it's the particle starting at position 0, which is plug in 0, 0 cubed minus 12 times 0, that is 0. And then draw it moving to the left. The first time it stops is at time equals 2. So we plug in 2 to the position, and we get -16. So it moves from 0 to -16. Then it starts moving again. And it doesn't stop after 2, but we stop caring after 4. So the next number we're going to plug in is 4. When we plug in 4, we get +16. So now, to figure out how far it moved, we have to add up the length of those two red lines. Well, the first red line, starting at time 0 to time 2, is 16 units long. The next red line is 32 units long. And so we're going to get 16 plus 32 units, which is 48 total units. So really, when we're looking at any of these problems, all of them all together, here are the things you want to be thinking about. The most important thing is that if you have a position, the derivative of the position is the velocity. And we didn't ask any questions about this, but the derivative of velocity is acceleration. And it's because the change in position over time is your speed, or your velocity, and the change in velocity over time is your acceleration. A positive velocity means moving in the positive direction. So if you define moving to the right or moving up as being the positive direction, if the velocity is positive, you're moving in that direction. And if you have a negative velocity, you're moving down or to the left. When the velocity is 0, the object is stopped, even if it's only for a little bit of time. And the total distance traveled is about the final trip odometer. Going backwards and forwards is the same in terms of it all adds to the distance. So one more thing we can look at. Not all objects move straight up and down or straight left and right. Sometimes they move in a curve. For example, here's a cannonball. So if an object is moving in 2 dimensions, we can actually use implicit differentiation to talk about its speed and acceleration as being built of 2 components, one in the x direction and one in the y direction. So here's a picture of the cannonball shooting in the direction it's actually going. And the actual derivative tells you the slope of the line that it's moving on. However, we can break it up into dx dt and dy dt and talk about its speed in the x direction and its speed in the y direction. And if you remember, if you have dy dt and dx dt, you can actually get dy dx by dividing the two, and that gives you the slope of the triangle to the left. So here's a question. If I have a cannonball shot from the ground, and it's going along the line y equals 32x minus x squared, and I tell you that it has a horizontal speed of 4 feet per second, then what is its initial speed in the y direction, and what is its initial speed in general? Well, remember that what we're looking to do is fill in this triangle. The base of this triangle is dx dt, and if you look in the problem, I tell you that the horizontal speed is 4 feet per second, so dx dt is 4. We want to know dy dt, and we want to know dy dx. And so what we need to do is take the derivative of this function here implicitly. So we're going to take d dt of y equals 32x minus x squared. Well, the derivative of y with respect to time is just dy dt, and the derivative of the right-hand side is 32 dx dt minus 2x times dx dt. Remember, when you're taking the derivative of x squared, you have to use implicit differentiation. Now we can pull out our dx dt and get that dy dt is dx dt times 32 minus 2x. Well, we want to know its initial speed. Its initial speed is when x equals 0, or it leaves the cannon. So let's go ahead and plug in 0 for x and 4 for dx dt. So what we get, dy dt, is 4 times 32 minus 0. 4 times 32 is 128 feet per second. So that's its dy dt. And now when we want to figure out dy dx, all we have to do is fill in this triangle. Well, here we don't actually want to know the slope. The slope would be 128 divided by 4, or 32. We actually want to know how big the velocity is. And in this case, what we're going to do is take the triangle and plug in 4 and 128 for the Pythagorean theorem. So when we do that, we get that the overall velocity is 128.06 feet per second. So that's it. Go ahead, try the practice problems, and I'll see you next week.